So just a little recap though, right? The first couple slides here, I want to just go back to some important points, right? If you had a bunch of blue things over here, little dots, remember that these dots are like bouncing around each other. They're bouncing into each other. And as they do so, they're kind of moving out toward this area of lower concentration, right? So their own kinetic energy is making them move around, and they're moving toward a space of lower concentration, right? Just because as they bounce here, they're bouncing off a little closer to here. As they bounce here, they're less likely to bounce backwards is basically what's going on for these, right? But it's their own kinetic energy, right? And you can tell that because if you add heat to it, you're adding more kinetic energy, right? That's what heat is. And that diffusion will go faster. Right? So you'll start from something like this, area of high concentration, to an area, to a flattening out of that concentration gradient, right? Where these guys are all still moving around just as much. If there's just as much heat, they're just not moving in any one direction, right? So they've reached equilibrium at this point. All right, so the thing you want to remember out of all this, right? It's a big concept, one of these major sort of concepts in physiology, that things move from a high to a low concentration. They move from high blood pressure to low blood pressure, right? This is a big kind of concept in physiology that will come up over and over again in a couple of different concepts, right? High concentration to low, or high blood pressure to low blood pressure is moving. Things are moving in that direction just as a natural sort of effect. So high to low. Always remember that, and how it applies in many different situations, right? That's diffusion, just across the space. And there was also movement into a cell or out of a cell, right? You have this high concentration here. Things are going to want to, if they can get in that cell, they will eventually come to equilibrium. That'll be equal concentrations inside and outside the cell, right? Over time, if they can get through. Right? So that is because there'll be this driving force, right? That diffusion, that chemical concentration gradient. If the concentration is greater in the cell, the force will be leaving the cell, right? Pushing things out of the cell. If the concentration gradient is greater outside the cell, the chemical driving force, the concentration gradient, will be driving everything into the cell, providing they can cross that cell membrane. So the whole concept of that high to low concentration, we're normally talking about different little particles in the fluid, right? In the water, in the solvent. Over here, you can think of sodium or chloride or something, or glucose, any kind of solute that is moving from a high to a lower concentration until it reaches equilibrium. Right? But then we also want to consider the solvent itself. Right? All these water molecules, they're all over, but I just put them over here. Right? If for some reason we look over here, there's less water molecules because there's more solute. So the driving force of the water molecules is going to be toward its lower concentration gradient, right? So that it'll start moving in the opposite direction of the solute, right? Until it reaches equilibrium, right? So this is still high to low, right? But it's osmosis, right? It's the kind of background of everything. So it's moving in the opposite direction of our normal concentration, solute concentration gradient, right? Sodium, chloride, hydrogen, anything like that. The water is going to be moving against it. Right? So that's osmosis, right? It's still moving from high to low, but from a water perspective, it's moving toward a higher concentration of solute, right? Everybody clear on that whole thing? Sometimes it's a little confusing because it's kind of moving in the opposite direction as everything else. The other actually thing to remember about osmosis is that it's movement across a cell membrane. Oh my God. You guys can't hear Siri, huh? whatever I say, something really activates Siri. Anyway, this, shut up. It seems like I'm insane because you can't hear it, but so across the cell membrane, this osmosis thing, that's another important point. It's movement of water across the cell membrane, not just like diffusion could be of solutes, could be across the interstitial space or across the cell membrane. Osmosis always has to do with movement of water across the cell membrane into areas of higher solute, which is similar to saying into areas of lower water concentration. So this movement, right, from water molecules toward an area of higher solute concentration. Also, some of the terms associated with this would be that this cytosol in this case, right, is going to create an osmotic pressure. And, you know, one way to think of this as far as osmotic pressure, because pressure usually, you're kind of thinking pressure is going to be going this way. You could think solutes suck, right? Solutes suck water, right? That's one way to think of this osmotic pressure. Solute's going to suck in the water like they're like a sponge, right? And so between the cells and the interstitial fluid or extracellular space, right, there's usually not a lot of osmotic pressure because we don't want a lot of water flowing into the cell or out of the cell, right? We want it at equilibrium. And so these osmotic pressures are associated with this tonicity of a cell or of a solution. And the tonicity is always going to refer to the solution rather than the cytostolic fluid. So in an isotonic, iso means same, there's no movement. Whereas in a hypotonic, that is very few particles in the extracellular space, water is going to move into a cell. In a hyper, above, like hypertonic solution, water is going to move toward that out of the cell. So one way to also remember hypotonic is just hypo, just think hyposalt, hyposalty, right? Hypo means less than, if you could think of hypothermia, right? You're cold. Hyposalty would mean that the water is going to move toward the cell, which has more salt in it, right? Hyper, above, hyperactive, it's a hypersalty solution, right? If tonic throws you off for whatever reason. All right, so that's osmotic pressure and tonicity, how it relates to osmosis. And then we talked about these fluid compartments, which is basically your, extracellular fluid, which will be your plasma, and your interstitial fluid over here, right? And for these two compartments, right, this is compartmentalized within the blood vessels, and you might have extra proteins and stuff in there, but in general, like your salt, your electrolyte concentrations were pretty much the same in between your blood vessels and your interstitial fluid, right? Whereas your cells themselves are going to have very different concentrations of like sodium and potassium right there, right? So movement from here is going to be often based on how permeable it is and the fact that water is going to follow salt. So that if you had for whatever reason, if you had a low blood volume, that is, you had less water in your blood might be very salty. That will lead to extra salty interstitial fluid. And then you'd have that hypertonic solution and water would start leaving the cell, right? So the movement in between these fluid compartments is also going to be based on like salt and water, well, basically tonicity or osmotic pressure and stuff. All right. And so the reason we get this sort of difference in between the inside of a cell and an outside of a cell, like over here, this is given some of the numbers here. Sodium and chloride, for instance, very low, 10 millimolar, 4 millimolar inside a cell, whereas they're very high outside the cell. Whereas potassium, very high concentration inside the cell and low outside the cell, right? And so this is basically, your selective permeability. Right? Your cell membrane is there to kind of keep your intracellular material of a particular environment. So you're keeping some things outside, you're allowing some things to come in, but not other things, right? So this whole selective permeability thing comes in to maintain this sort of gradient of the particular electrolytes, right? And so there was kind of two aspects of what we talked about with this permeability, right? You had the lipid bilayer itself, which was you had hydrophilic phospholipids touching the water, and then hydrophobic fatty acid tails, right? In the middle, so that molecules, very small, like non-polar molecules, can get through this space very easy, right? So they can diffuse right through the membrane. Hydrophobic molecules, bigger ones, can also get through easy because they like that whole non-polar aspect here. Very small, even if they're a little polar, if they're small enough, they can get through for slightly more complicated reasons, but they can get through. Let's just accept that. Whereas bigger molecules like glucose, especially if it's polar, are not going to be able to get through that membrane. Amino acids, which have a charge to it, and certainly ions, which really, even more so than these polar molecules, don't like non-polar regions, or non-polar doesn't like them, however you want to think of it, right? So they won't get through this lipid bilayer. They're soluble. They like water. They don't like going through this hydrophobic region. Such your lipid bilayer, but I mentioned that there are also protein channels embedded within, right? Your cell membrane is not just lipid. It's not just the lipid bilayer. You've got embedded proteins of all sorts, but you've also got these channels and carriers and stuff that are going to make the membrane more permeable to certain things by allowing certain things through. Right? So this gets us into our whole transmembrane protein stuff today, right?